Hey, welcome to According to Pete. I got a long list of notes today. In our last episode, we talked about UARTs, Universal Asynchronous Receiver Transmitter, UART. They get used in with GPS sensors, and communication is usually that. Cellular cell modules are usually using that. Today, we're going to talk about SPI, or SPI, and I2C. SPI stands for Serial Peripheral Interface, and I2C is Integrated Circuit. These two protocols are used in a lot of our sensors. I'm going to try to cover important basic parts about what these interfaces are without getting too deep in it. Oh man, I could talk for months about these two. I don't know how we're going to cram this in, but I'm going to try to cram in as much as I can. I'm going to start with SPI, or SPI. It's defined by 4 lines, okay? You got a line called meso, mosey, lines called meso, mosey. There's a chip select, or slave select, and then there is a serial clock, SCL, okay? Meso is master in, slave out. The other one, mosey, get this, master out, slave in. The microcontroller would be designated in the example that I'm going to give as a master. It initiates the contact, it generates the clock, and it sends data out on the mosey line, master out, slave in. It sends data out to a slave, and data comes back from the slave on the master in slave out line. Then there's the serial clock line, right, which is just a square wave, and again, I'll show you this in the diagram. And then there's the slave select line. The interface is able to have multiple slave devices on the bus by using different chip select lines, slave select lines. Now, I'm going to show you a timing diagram of a part called, it's from Analog Devices, AD9837. It's a signal generator chip that I've been playing with. And it's a little different. I don't mean to confuse the issue with SPI ports, but you know what? Everything's confusing about SPI ports, and I'll kind of illustrate that as we go through the timing diagram and everything else I'm going to show you. So this is the timing diagram for the AD9837 signal generator chip. This top line is called SCLK, serial clock, and you can see it's a clock signal. The one below it is called F-sync. There was no F-sync in what he just described. What's that all about? And then there's S-data, serial data. The first thing to know about the standard of SPI ports is that there really isn't much of a standard. Depending on the manufacturer, they will set the parameters of this port very differently. They won't even call the lines meso, mosey, chip select. In the case of the AD9837, SCK that you might find on a processor is called SCLK. Okay, I get that one. F-sync, that is equivalent to the chip select line, and that might not be completely obvious until you realize, okay, to make the SPI port work, I have to have a select, and the select has to be active for the duration of the communication. Well, that looks like that one. Then there's a data line. This happens to be serial data, S data, right, makes sense. And this is only going to, this is the equivalent of mosey, master out, slave in. On this particular part, there is no data coming back from the part. And I apologize for that, but this is a pretty good illustration of how loose the SPI standard really is. What can you take away from this? To initiate an SPI transfer, SPI transfer, the first thing that happens is that your chip select, which in this case they call F-sync, has to go active. In this case, it is active low. And in most cases, the chip select, or in this case F-sync line, are active low. Doesn't have to be. You have to, when you're setting up SPI communication with any given part, you got to look at the data sheet and go, okay, how do they want me to talk about this, or to communicate with it, I'm sorry. And in this case, F-sync goes low, and then you put data on your line, meaningful data, right? So it's either high or low, and it sends it out. In this case, the part sends MSB first. I'm trying not to confuse this, but it's really difficult. So let's talk about the data line for a second. In this particular example, you got D15 over here, and then you got D0 over here. This is a 16-bit transfer while the chip select, or F-sync, is low. That is a very pliable thing. For the microcontroller that you're operating with, you can define this data frame to be anything from like 7 bits or less to, 24 bits. I mean, it's really all over the road. And for that reason, the hardware does not fully commandeer use of a select line because they know that you're going to have to adjust those timings. So you have control of the select line manually in most cases. And then there's the S clock. Depending on the part that you're trying to talk to, you can either set it up to read data on the low going edge or on the high going edge. Like I say, the standard is very, very loose. The timing diagram, it's full of things like T1, T2, T3. Talking to the AD9837 has requirements, right? For example, S clock has to be high for a certain period of time defined by T11 before the F sync or chip select line goes low. And then there's this, okay, so before S clock goes low on its first clock, you have to observe T7. What this illustrates is minimum timing. And the minimum timing will define how fast or slow, how fast you can talk to it or how slow you have to talk to it. Bear in mind, all of these numbers, T8, T4, T5, right, they define a maximum clock speed. So if you're setting this thing up in hardware, you need to look at the time, the longest time that you have to wait for any given transaction and set your clock speed accordingly. In my case, and in the example that I'm going to show you, I actually bitbanged this. I did not do it in hardware. I did put it on the hardware lines because I assumed at some point I would want to go to hardware. Honestly, this transaction is pretty easy to bitbang as long as you're paying attention to, where you have to read data or where you send data. And it's not that bad. The thing to take away from this is this defines how fast you can run the clock by the longest time that any given thing is. I did mention earlier multiple slave devices. So check this out. SPI ports can support multiple slave devices by virtue of the chip select line, which in this case is referred to as F-Sync. Just about all SPI port devices, when you take the chip select line into its inactive state, which in this case is high, and it's generally high, but it can be low depending on the device. When you take it to its inactive state, its data output lines and data input lines go high Z, high impedance. What that means is they won't be interfering with other devices that are on the bus, okay? So you just take this line and turn it off, and then you take your other line that goes to other device and turn it on, and now you're talking to that device, and you don't have to worry about this one. But the message behind SPI that I really want to get down is, wow, this is a really loose standard. The things that they all have in common, or generally have in common, is there will be a data in line, there will be a data out line, and there will be a clock, and there will be a chip select. Beyond that, you oftentimes have to look at the data sheet for what you are going to be communicating with, and you have to set it up accordingly. In this case, it wasn't so difficult. In other cases, it will be much more difficult. I just want to point out the hardware that I'm working with here today. For my SPI example, I am using this guy. This is something I've been working on with somebody named Ann Mahaffey, who used to work for Analog Devices. And this is the AD9837 signal generator chip, which we have configured to act as a shield for an Arduino Pro Mini. There's the chip, there's an op-amp out, there's a big old crystal. Anyway, this is the thing that we're playing with today, and this is the first example for SPI. Now, since I'm here, I'm going to point this one out too. This is my HMC 6352 magnetometer or compass. It's an integrated compass module, yeah? It gives heading and stuff. So I've got these things running, and I've got them hooked up to a Saley logic analyzer. We do sell this guy. TOL 08938. I think it retails for something close to 150 bucks. Very handy tool when you don't know what your logic is doing. Scopes are great, but scopes are harder to configure. So this is the pertinent code of talking to the AD9837. This is an example of a single 16-bit data transfer to that part. This is the bitbang. I did not use the Arduino SPI library. To bitbang like this, you have to go back to the timing diagram that I showed you before. Two things to note. Number one, the clock frequency on the Arduino Pro Mini is 16 megahertz. Now, if you invert that and you take the period, it's like 62.5 nanoseconds? That's right. What that 62.5 nanoseconds means is Nothing gets done in less than that amount of time. In fact, it usually takes more than one clock cycle to do anything in a microprocessor. So as my upper bounded limit, like nothing's gonna get done faster than that. I know that, that's an absolute. It's not an accurate number, but I know nothing's gonna be less than that. Now the timing diagram of the part, the 809837, all of its minimum timings are in nanoseconds, like single digit, some double digits, nothing that even approaches 62.5 nanoseconds, right? So the point of that is I can bitbang this thing and I don't have to worry about delays because I'm never going to, as long as I'm doing one thing per instruction, I'm never going to come close to that minimum limit. The first thing you do, digital write fsync low, right? I'm saying, all right, I'm gonna talk now. And then I just go into a loop, a 16-bit loop, right? So I'm reading my variable, which is dat, D-A-T, which gets sent to this function, and I check the most significant bit, and if it is set, then I write the S data line over there as a high. If it's not set, I write it as low. Then I clock, digital write SCLK, low. So it's down for one, and then it's up. Okay, and like I said, I don't have to worry about the timing of this because all those minimum times were much, much smaller than anything the processor is going to be capable of doing. Then I shift the data 1 bit, and I run that through 16 times, and then I write fsync high. Fantastic. In the case of the 809837, you have to do this 5 times. The first one, you have to send it, and I'm going to say hex values 0x2100. This command basically shuts the thing off and gets it ready to change its parameters. Then it sends, and this is a little confusing, there's 28 bits. It sends the lower 14 bits, LSB, and then MSB, but the trick is it's not sending bit 0 first, it's sending bit 13 first, and then it scrolls through to bit 0, and then it sends bit 28 or something, and it's still a 16-bit transfer, but the upper 2 bits are 0. So we send the command, then we send the lower register, then we send the upper register of the frequency bits, and this value has to be calculated in a funky way that's not pertinent to the example, so I'm not going to bother. Then you set the phase register, because the generator is capable of doing all kinds of wiggy things, which I'm not trying to do in this case. So I send this as 0, and then the very last thing you do is you send it 0x2000. And the particular part, actually, this is for a sine wave, so if you can send it a square wave by changing, 1 bit, or you can send it a triangle wave by, doing it another way. But this is the full command sequence that we're going to be looking at. The point of this is this little bitbang gets run 5 times to send a full set of instructions to get the chip to do anything. So I'm going to take you over to the logic analyzer, and we're going to look at this, and I'll show you this. Can you see this thing right here? This is awesome. This is the Saley logic analyzer. It's got 8 lines in, and on the first 3, I've got set up my SPI example. You can see, you can go over here to settings, edit settings. When you go to this thing, you can set it up as a SPI port, and you can assign the channels, which is really cool. And then you can assign all the wacky bits that I was telling you about. Most significant bit first, standard, or you can change it to least significant bit first. 16 bits for transfer, or oh my gosh, look at all, yeah, it's nuts. Clock is high when inactive, data is valid. So yeah, like I said, all this stuff is really, really wacky. Now, a minute ago, I told you that to talk to the 809837, you have to send it 5 16-bit transfers. What we're looking at here is the first 16-bit transfer. The analyzer, because I've set up its properties correctly, it can interpret the data. And as you can see right up there, it says 0x2100, which, as I said, is the first byte that shuts down the chip and gets it ready for further commands. Now, if you look at the waveform specifically, this is our enable line. So this guy goes low, and then the clock goes low after a bit, and it reads the data on the downgoing pulse of the clock. So if you look at this, that's a 0, that's a 0, that's a 1, and that's a 0, which is binary for 2, right? Because you get 0, 1, 0, 0, that's a 2. And then you get 0, 0, 0, 1, Well, that's a 1, 2, 1. So check it out. And then all the rest is zeros, and it's just telling you up front there. Now, this is the first byte. With the mouse wheel, I can pull back. This is our next example, so don't look at that thing. But there's a very long delay, and this delay is here because I wanted to look at something in the code before it gets to the next 4 instructions. So now I can zoom in on that action. Check that out. The next 2 transfers are the LSB and MSB of the frequency register. And so I have not accounted for those values. It's going through a calculation, whatever. So that ends up being 4189 in hex and 4001 in hex. So that's the frequency information. Then there's the phase register, which is this guy right here. And as you can see, the analyzer has interpreted that correctly as 0000. Here's all the clock pulses. Here's the enable line, right? It goes high for a bit, then it goes low again. Okay, here comes the next 16-bit transfer. And it's like bits 16 or 15 through 0, and those are all zeros, as you can tell. And my last transfer, and I'm doing this all with the mouse wheel, so pretty cool. Here's the power up command again, 2000, and you can go through the waveform again, 0, 0, 1, 0, that's a 2. And the rest of it going out is 0. And that's the full SPI setup. One other thing you can take from my example, my data line, I've left it low between the byte transfers. That's poor form. I should really have that tied high, and that's a failing in my Bitbang. I should tie that thing high again when I get out of the transfer, but I didn't. But remember, you've got a master out, slave in line, and in most cases you have a master in, slave out line. Doesn't happen on this particular part. You'll have a clock, which is generally active low, and you'll have an enable line, which is generally active low. Now, let's talk about I2C. Now, this is a timing diagram for the HMC 6352, which, there it is. Now, before I talk about this, let me talk about what the I2C standard actually is. Instead of 4 lines, you have 2 lines. One is it's SCL, which is serial clock. The other one is SDA, serial data. The thing about these 2 lines, they are bidirectional. They are not just, either send or either receive. They have to do both. They are also open drain, which is to say that they don't have a direct line to VCC. They have a direct line to ground. And then externally to your parts, you have to have a pull-up resistor. This actually supports not only multiple slave devices, but it can support multiple master devices. So in this example, over on the left here, you see SDA and SCL. So if you're actually probing the 2 wires of interest, these are the waveforms you would see. Now SCL is just going to come from the master, so that's not going to do anything wacky. But the SDA line is bidirectional communication. So if you look down here, you see MSDA and SSDA. I'll give you 1 guess, well, 2 guesses what those mean. Master serial data and slave serial data. So what happens, right, the master is talking for a little while, and then after a bit, the slave is talking for a while. It's an output on your microcontroller. The SDA line is an output for this length of time, and then they change it to an input, and then it's receiving data being latched according to SCL. And then up here, you have the resultant waveform of MSDA and SSDA. Let's talk about how data transfers from a master to a slave, or how the communication works. To begin any kind of data communication on an I2C bus, a master device has to issue a start bit. And a start bit isn't a start bit in the classic sense. It's not going to be like, a clock distance here. What it actually is SCL and master SDA, what happens is the master sends serial data low, a low going transition, while the clock is high. All other transfer or transitions of data of the SDA line occur when the clock is low. If the clock is high and the SDA line is changing, that means it's either a start bit or a stop bit. So if you look over here, you can see, okay, SCL is high and the master takes SDA low, and that's a start bit. Now, if you go all the way to the other end, SCL is high and the master takes SDA high. That's a stop bit. This is how the device recognizes start from stop. And this is how the master device maintains control over the bus against other masters or slaves or what have you, against marauding masses, who knows. Now, the very first thing the master will do after initiating the communication is it will send out a slave address. It's generally 7 bits long, but it can be longer, and you'll have to configure that in your hardware if it ends up being. But the vast majority of parts that I've seen work with the 7-bit address space. What this thing does is it sends out 7 bits of address, and then it sends out 1 bit that indicates if the master wishes to read from the part or write to the part. So 7 bits of address and then read or write. After that, the slave sends an acknowledge. The master lets the SDA line go high, and then it listens, and the slave will go, okay, I heard you. So in this case, sends out 43 hex. The address is actually 21 with the read-write bit set to 1. So here's our start bit, and then the device reads on positive going edges of SCL. So look at master SDA right here, and you've got 0, 1, 0, 0, which is 4, 0, 0, and then a 1, which is the last address bit, and then a 1 indicating that it wants to read, because it says read right there. So now the master lets that line stay high, and then the slave goes, okay, I got it. And then the slave starts transmitting data according to the SCL lines. Because these lines are bidirectional, I way did not want to bitbang this. And in fact, I haven't done too very many I2C interfaces in the first place, but I did get a fantastic example from Adam Meyer at builder.com.org. I can't remember. Adam, I'm calling you out, man. This is some handy code that set me up real quick. It was an example specifically made for the HMC 6352, and it was cake to make this thing work. A couple other notes before I describe this. You can bitbang an I2C port, but it's not really, it's not pretty, right? There are like 4 different modes that you would potentially have to coordinate, you know, master transmit, master receive, or in some cases, you may want your micro to be a slave. So you're going to have to deal with slave transmit and slave receive. What a pain. I mean, you're going to have to deal with that anyway, whether you're bitbanging or not. Cool things about I2C, and yes, I am looking at my notes because it's really hard to keep all this junk straight. Standard timings are pretty well defined. There's no like phase and polarity junk that you have to worry about with your clock or your data. It's always going to be the same. So that's pretty cool. The standard is not all over the road the way that SPI is. Here's the bulk of Adam's code. And you will find this example on our HMC 6352 product page. I think it's at the bottom of the list of all the examples and stuff. And this is it. Right from his website, it rocks. So in the setup, you do wire begin. It's called the wire library. I was looking for SPI, or not SPI, I2C library. Doesn't exist. It's wire. In the setup, you do wire begin. And then you will see in his example, he does this, HMC 6352 slave address. And Adam, I can't tell you how much I love writing out long variable names. But this slave address, right, if you look at the data sheet, it says it's 42. And it's actually, see, what he does is he shifts it down 1 bit. So the 42 becomes 21. The reason is because the Arduino code, when you start transmitting to this, it's going to automatically shift that value and then add the read-write bit. In the loop, we have wire begin transmission, and it goes to this address, which is now 21, and we want to write to what he's got set up as the read address. It's basically the A command, which if you look at the data sheet, the A command says get heading data. And what this will actually do, begin transmission, write the A command, and then end transmission. So these 3 guys, what this does is it takes heading data and it puts it in the right location for the next bit, which just reads it out of the part. And then a delay of 6 milliseconds. This is, again, if you look in the data sheet, it says, okay, it takes this much time to load all that junk into the right read address. And then there's this guy, wire request from the slave address, 2 bytes. And then it just loops, right? So he just comes around, once you get that data, and he reads it, and he sends it out to the serial port so you can read it. And then it just comes back up here. sends the A command again, loads new data. And that's it. Here we are with the Saley Logic Analyzer again. I will show you the edit settings. This is really simple, right? You can you can define what which lines are which, and then how you want to display the address. There's no polarity issues. There's no you know, where it's going to read the data, where on the clock it's going to read. It's all standard. So that's pretty awesome. And the analyzer can read all this junk for you, which is also really, really awesome. Let's talk about the example that I showed. The code, the very first thing it's going to do is going to transmit the slave address plus the read-write bit, then get an acknowledge back, and then it's going to send the A command, and then it's going to stop transmission. So this is the very first thing I've got laid out here. Now the analyzer, as you can see this little green dot, hey, that's a start bit right there. Check that out. And over here, whoa! So really powerful tool. I love this thing. So there's our start bit. And then you remember how we shifted the data 1 bit, because the code, the internal code that you don't see, is going to shift that automatically and then add the read-write bit accordingly. And that's exactly what's happened here. So the 42 that became 21, well, back in here, it's now 42 again. The analyzer has interpreted this thing as 42. So let's check the transitions. And remember, of course, that the SDA line that we're looking at is a combination of the master serial data and the slave serial data. Here's our start bit. On the first clock edge up is a 0, then a 1, then a 0, and a 0. That's 4 in hex. And then a 0, and a 1, and a 0. And that's 2. Now what that actually is, the slave address of 21 plus the 0 write bit. And then there's one more guy here, and that's a 0. That is the slave saying, okay, got it. Now this little bit here, this is the transition between our transfers. So this, the analyzer has seen, oh, this is an A. So it's indicated that I'm sending an A plus acknowledge. So it's counted out the 8 bits of the data transfer, and it recognizes this last one, that's a low bit, that's the slave again going, right, got it. And then we go out. There's the stop bit. So now I'm going to pull back, and remember there's 6 milliseconds delay to load the registers. This is the time indicator, and if you look up in this corner here, right there, 6.012 milliseconds. Hey, close enough. So this is the delay that I showed you that was 6 milliseconds. Let's zoom in on this guy. The first 2 bytes are going to be heading information from the HMC 6352. Now, this will vary according to which way the wind blows, effectively. The first one is actually the read command. I'm sorry, I was being stupid. So then you set up slave read, and that's what that guy is. There's our start bit. And the 2 bytes after that are heading data. So you'll get the command, which if you look in the data sheet says it's, 43. And the analyzer has seen an acknowledge. There's the acknowledge right there, the very last 9th transition. That's a 0. And then the next ones, there's the next byte here with acknowledge. Now check this out. The very last one, I wasn't sure what was going on at first. This is the last heading bit plus NAC, which is a negative acknowledge. This is how you come out of a read operation with the HMC 6352. So not a big deal. This is doing what it's supposed to, and there's the end of the transmission. I would recommend sticking with the Arduino code to do I2C because it's crazy complicated to bitbang that junk. So that's it. I really hope that was helpful. I'm trying to think now about anything I may have forgotten. I probably forgot a slew of things. That is SPI and I2C in ragged, horrible, unbridled nastiness. Until next time, keep the questions coming. You can send them to feedback@sparkfun.com with according to Pete in the subject line, or you can add comments below. Hey Pete, you're an idiot. And I'll see you later. Bye.